Good morning, good afternoon. This is Emmanuel from the SIMBA team. Thanks for joining the webinar. I see some friendly faces in the attendees list, so welcome everybody. I think we can wait maybe 1 minute uh, before we get started because I think people are still getting connected. Hello, Guillaume.
Hello, Emmanuel.
Doing
Hello,
good?
everybody.
Hello everyone.
Hi, Adrian. Good. So I think we can get started. So welcome and thank you for joining the release party of SIMBA 25.03. This is kind of a big release. We've been working hard with the team on this one. So that's why we wanted to celebrate this morning. It's a little bit early to have to drink something else than coffee for us. But the intention is there. If you don't know us, my name is Emmanuel. I am the CTO and the lead developer of SIMBA. I have the pleasure to be with today with Guillaume and Adrien. Guillaume is our power electronics expert, and Adrien is our power electronics support engineer. So today, so first of all, we'll try to do a quick webinar, probably around 30 minutes. We will start with a quick overview of PowerSys and SIMBA. If you don't know us and you don't know why you're here, we will explain you what we do. Then we will cover some of the main features of 25.03. We will start with the signal calculator and with some other updates regarding the UI and other things. And finally, we will cover the kind of the main feature of 25.03, which is the dual-stage electro-thermal analysis. We will show you what it is, what are the benefits, and we will show you, of course, a lot of examples. At any time, I'm pretty sure you can ask a question using the Zoom chat. So at any time you can ask a question, and at the end of the webinar, we'll have a time. We'll have some time for some questions and answers. Okay, so PowerSys. So the three of us are working for PowerSys. We are kind of a French-American company. We are specialized in electrification, and we are experts in model-based design simulation software. We have two main products, GEMAG for electric motor design, and SIMBA for power electronic simulation. We have offices a little bit all around the world, in Europe, in North America, and in Asia. We have a team of about 30 engineers located all around the world. Sorry. So SIMBA. So if you don't know SIMBA, that's good. I will try to explain what is SIMBA to you in a couple of minutes. So SIMBA is a power electronic simulation software. It can be used in any type of application. Everywhere you have basically a semiconductor or a switch mode power supply, you can use SIMBA to help you design your converter. It can be used in electric vehicles, can be used in energy system, in defense, in drone, transportation, home appliance. We have use case a little bit everywhere. It can be used to help you design your converter by looking at power quality, thermals, efficiency, semiconductor selection, topologies, post-mortem operation, trying new ideas and comparing different scenarios. It can be used to help you design your controller by looking at continuous system, discrete system, C code, stability analysis, motor drive, control strategy, and so on. And SIMBA can also be used for detailed simulation. So you can now use SPICE model inside SIMBA to run detailed simulation, look at detailed transients, look at EMI, gauge drivers, and so on. The type of study you will usually do in a SPICE simulator. On the left-hand side here, you see a small video of our user interface. We try to have it as simple and powerful as possible. But SIMBA can also be used with scripting, and we will cover that in a moment. So to illustrate what SIMBA can do, I have three kind of setting points for SIMBA. The first one is in SIMBA, we have different models of power switches. We have first idle models with XML thermal description, the type of model you will find in tools like in Simulink or Simscape. And you can use that for system level simulation. But SIMBA also supports detailed models. As a matter of fact, we can import SPICE model from semiconductor manufacturer. And that can be used for switching level simulation. And this is a good thing about SIMBA is you can switch between one model and the other without having to switch tools, and you can stay in the same tools. To illustrate this, here is some waveforms that were simulated with SIMBA of a buck converter, VDS voltage. And we compare the waveforms with the idle model that is super fast, but not so accurate, with detailed model that is probably a little bit slower to simulate, but with way higher accuracy. Second selling point of SIMBA is our capabilities for motor drive simulation. We have excellent motor model thanks to our partnership with GEMAG and GEMAG RT that you can use to have very high quality, high form, almost as precise as a finite element model, but in a circuit simulation, and also very accurate loss analysis inside the motor. And you can use that for a lot of different types of scenario, including building efficiency maps. As a matter of fact, with SIMBA, you can do a multi-objective optimization of an entire electric drive unit. So you can optimize the controller, the motor design, and the inverter inside the same optimization loop. The third selling point of SIMBA is our Python module. The Python module of SIMBA is native, and this is really important. That means that it's not a bridge that will connect to another a native desktop application. It's native. It can run without user interface, and it can run in a parallel environment extremely easily. To illustrate this, here is an example of an optimization script that we build to optimize the value of the LLC, of the tank values of an LLC converter. And with our Python module, you can run thousands and thousands of cases in parallel. And Python is excellent for post-processing, for pre-processing, and we try to have an API that is extremely natural and easy to use. We have auto completion. We try to give a very good development environment for Python. Okay, cool. So that was a quick introduction of SIMBA. Now we will start to cover the new features of SIMBA 25.03, and I will let Adrien explain us what is this new signal calculator.
Thank you, Emmanuel. I will just share my screen.
Oh.
Yeah.
How do I stop share?
Normally, I have sent you the requests.
Yeah. We can probably share now.
Yeah. I think it's fine. Do you see my screen?
Yes.
Okay, perfect. So hello everyone. I am going to introduce you the new signal calculator amazing tool in SIMBA. So for that, I prefer directly to open the SIMBA desktop version. So basically, the signal calculator tool is a new tool allowing you to post-process all the signals that you want to manipulate. So basically, if you want to make some mathematical equation or apply any ratio or multiply any parameters each other, you can directly do that in the signal calculator tool, and it will directly show you the result of the combination of your signals. So the interface is quite simple. So here you have the signal variable section where you can add all the signals that you have selected in your result tabs. You have the jobs that you have previously run, and you can select if you want to check the diode current, inductance current, or any other signal. You have the functions available if you want to go into the through math category, trigonometry, or integral as well. And inside each category, you have sub functions in order to have the basic functions that you can use for post-processing purpose. And here you have the equation. It means when you are going to select any signals, you can directly manipulate them inside the equation section. And at the end, when you are going to calculate, to click on the calculate tab, you will have a new calculator functions with the equation that you have performed. So let's do a quick example. So here we have a basic three-phase system with a bridge diode, and the goal of this example is to calculate the RMS, the apparent power, okay, of the system. So basically, I am going to select my voltage VAS and my current through the inductor. If you click again into the signal calculator, you can see the two signal displayed here. So the current and the voltage. Of course, you can rename directly the signal with the name that you wish, like this. Okay. And you can add them to the equation. For example, if you just want to make the multiplication of both signal, you can click on plus, and you can just click on multiply with your keyboard and plus, and here you will have the new signal displayed, which is equal to the multiplication of current versus and the voltage. Or what you can do, and here I want to measure the apparent power, so it means I need to calculate the RMS value of the inductor and voltage, and I need to multiply everything by 3 because we are in three-phase system. So basically, you can click on add function, and here you have the equation of the RMS equation. And if you click on this button, you will see that X corresponds to the variable name and Y is the frequency. So we have 60 Hz here, and X corresponds to the variable name displayed here. So here I am going to change X by IL1. Then I want to multiply this again by the same RMS function, but now I want to get the voltage. And finally, I want to multiply by 3 because I am in a three-phase system. And now I can give a name power apparent like this, for example, and you can click on calculate. And if you go back now, maybe I can just delete this, and you can see now the apparent power is close to 2133 volt ampere. And if you want, you can compare, because in this example, we have a power three-phase probe giving you directly the apparent power. So if you click now on these signals, you can see that both value provide exactly the same result. So it's just to show you, we have the probe available directly with the block, or you can make any mathematical things and manipulate all the signal together in order to get the same result. So I guess this tool will help you a lot if you want to manipulate, and if you don't want to use Python, you can do everything now in the graphical user interface. Perfect. And now I am going to present you the new updates of this 2025 March version. First, we have enhanced the SPICE netlist compatibility. So now we are supporting additional primitives and models. For example, we are supporting table syntax, as you can see directly on my screen. We are now compatible with charge-based nonlinear capacitor, and we are also compatible with B source SPICE model as well. So all this new improvement simplifies migration from other tools, from LC SPICE, for example, in SIMBA, and we also enhances the flexibility when building or reusing existing design into SIMBA. We have improved also the user interface. Now you can see that the symbols of each component are directly displayed into our library. So you don't need to drag and drop each component. You can see directly the meaning of each component when you are going through our component library section. And also the background of the result tab is in white. Before it was in black color, but now it is by default in white because some customer made these requests. So yeah, some of these changes now streamline simulation setup and post-processing workflow, and just give some new functionalities into this new SIMBA version. Also, regarding the Python API, now we can directly add a new Python code, okay, as you can see on my screen again here, in order to mirror the GRI progress tracking. So you can monitor directly the status of the simulation and check at which percentage you are directly into the simulation. And the stability of SIMBA also has been improved because when you are displaying a large number of signal, all those signals are stored into the RAM, into the computer RAM. Okay, so a new prevention mechanism has been implemented. So if the allocated memory reached 95% of the computer memory, a new warning message pop-ups in SIMBA result tab will be shown in order to prevent any potential crash. And you can see just the pop-up message. Okay, so it will just give you better stability and avoid to get any crash. And also we have simplified the multi-user licensing system for our customer who use a multi-user license. So whenever free seats are available, new license requests automatically activate users. So the users are automatically activated when free seats are available. That's the main things. And now Guillaume and Emmanuel will present you this amazing new functionality as well based on electro-thermal analysis simulation. Thank you.
Yeah, thanks a lot, Adrien. I'm also going to share my screen in order to keep in this presentation. Okay, all right. So I'm going to say a few words about the introduction about these new features. You will see that it's quite amazing. So about the principle, so one of the biggest challenge with electro-thermal simulation of port converters is the required computation time. Indeed, okay, long durations are necessary to simulate the thermal behavior because of the thermal time constants, whereas small time steps are required because of the simulation at the switching frequency scale. But if we can consider that the influence of the temperature, and especially the junction temperature, on electrical waveforms is very, very small, especially if we consider simulation at the system level. So that's why we propose here a new approach that we have named the Dual-Stage Electro-Thermal Analysis. And the principle is quite simple, actually. So first, we perform a simulation of the electrical circuit. That's the electrical stage. So here we use small time steps over a short simulation period, which leads to fast and accurate results. And from this simulation of the electrical circuit, all the switch currents and voltage are stored during the last switching periods, which makes possible to compute the loss of the bar switch in the second stage, which is the thermal stage. So here, for this second simulation, I would say, we use longer time steps, which makes it possible to get very, very fast simulation. And please note that here we assume that the junction temperature is constant over a switching period. So here, this is the small assumption which made. And you will see that it's quite impressive because it makes possible to speed up simulation between 5 to 20. So let me show you a first example before Emmanuel takes the floor. So this is a dual active bridge converter. You can see here the two converters. So here in the MOSFETs, these are ideal MOSFETs with thermal description here of SiC MOSFETs. So for this first stage and also for this second stage with here a second reference of SiC MOSFETs, the thermal description are here. You can see here the thermal impedance and the loss for the conduction here. And also for the switching energies that turn on and turn off. Okay, so let's go back to the design. So here, let's try a first simulation, but without enabling this option of the dual-stage electro-thermal analysis. Okay, so let's try to run this, and you will see that it's quite long. Let's try to see the results. So I'm going to plot the output voltage of the converter. Okay, and now the junction temperature of the first switch of the first stage. Here we are. So here you can see that the steady state of the electrical waveforms has been reached quite quickly, actually, but which is not the case of the temperature regulation of the thermal circuit. So here we find that it's a little bit pity to simulate all this circuit just to observe the junction temperature. So let's stop this simulation. And now let's try this option with the dual-stage electro-thermal analysis. You can look like here, you can see that here it's required to specify a second end time. So the first end time is for the electrical simulation. So here you can notice that at 10 milliseconds, the steady state has been reached. So let's specify 10 milliseconds. And I will keep the 650 milliseconds for the thermal stage. Right? Let's try this. And here we are. So we had the first part at 10 milliseconds, and now we've got the second part of the thermal. You see that the difference between the two computation time is really, really impressive. And now you will see that it will be also quite incredible with the examples that Manu is going to show you, because it uses Python scripts which run several simulations, and the gain is even more.
Thank you, Guillaume. I'm going to share my screen. Here you go. So there was an example that I want to show. I think I have a slide about it. Okay, is about motor drive efficiency map. So what it is, so first you model a motor drive, so with an inverter and a motor model. Here we use ideal switch model and thermal description files from Wolfspeed, it's SiC MOSFET, and we use JAMAG RT to evaluate the motor losses and the motor efficiency. And what we want to do is to run a simulation to evaluate the losses and the efficiency in both the inverters and the motors. But we don't want to do that for a single operating point, because when you have a motor drive, the actual current uh, uh, in your MOSFETs, both the frequency and the uh, and the amplitude are function of the torque, the speed, and the control strategy, and many other parameters. So in order to have a very good overview of the quality of your motor drive, you want to evaluate this on multiple operating points. And one way to do this is to build a map where you have the torque as an axis, the speed as an axis, as another axis, and the actual efficiency of your drive plotted. So there is the corresponding SIMBA model, which is kind of multi-physics. We have our controller here, we have our inverter model here, we have our thermal model modeled here, we have our motor using JAMAG-RT, and that's pretty much it. So the good thing about the dual-stage electro-thermal analysis, what I want to point out is, since we are in SIMBA, we like to to simplify your life. So to enable it, you just click a button. That's all that you need to do. You click a button and automatically we will analyze the circuit. Automatically, we separate the thermal circuits from the rest. Automatically, we run the simulation, we save the steady state waveform, and then we reapply them in the thermal simulation. So it's just one button for you, but in the background, we do a lot of stuff to make this happen. Because in the end, it's not rocket science. It's kind of a very kind of simple concept that we have implemented. It's just that we have implemented in a way that it's extremely simple and easy for you to use it. So now we can run it there. And again, so dual stage is here, and we can look that for instance, if I look at the current, do we have the current somewhere? Or maybe just the speed. We can look at the voltage. So here we simulate in the electrical world a few electrical cycles. And if I look at the junction temperature, we can see that it takes about 10 seconds of thermal simulation and to reach the thermal steady state. And here we see that the electrical simulation will stop after 2 electrical cycles. But the thermal simulation, if we don't specify anything here, it will stop whenever the thermal steady state is reached. We have an algorithm that performs FFTs and that detects when a steady state is reached. So you don't have to specify, if you don't want to, an end time for the thermal analysis. So now let me show you the script that we've built to study this. And of course, I have not prepared it. It's there. So this script, what it does, it's so first, it's open source. It's on our website. Everybody can access it, like everything that we do. So first, it will use 15 points of speed, 15 points of current. So it's about 225 cases. And for every speed and current point, it will use MTPA algorithm and flux weakening algorithm to get the actual command for the controller. And then it will run the simulation of a few cycles, get the losses, and save it. So let me run that for you because I find it extremely impressive. So here we are running 225 simulations of that motor drive. For every simulation, it's not a baby simulation, it's a real simulation where we look at actual waveforms. We take into account all the parameters of the thermal description files. In this case, it's the gauge resistance. We simulate in detail the losses in the motor. And in order to get the efficiency map, you will see it takes about 40 seconds. So in 40 seconds, we are able to get a very good view of the performances of that motor drive. And it's over. It took, in this case, 35 seconds. We have a 24-core machine, so it's kind of a heavy computing machine, but it's not like a crazy computer. It's a computer that you can buy for, I think, less than 2,000 euros. And we can look at the output. So we have a script for that. And I'm going to run it now. And it's analyzing the data right now. And here we got, the losses and the efficiencies of our inverter and of our motor for that particular point. And if I change a gate resistance, the DC bus voltage, the ambient temperature, the motor, it will take 40 seconds to get a new efficiency map. And you have nothing else to do. So I found it pretty impressive. The other example that I wanted to show you is related to Monte Carlo analysis. So here, what we want to do is we want to show what is the influence of the current distribution of parallel MOSFETs on the losses and the junction temperature. So you know that it's common to stack MOSFETs in parallels to allow higher current, but because of the nature of the MOSFETs, the RDS(on) value in the different MOSFETs can be a little bit different, right? You have a tolerance, 5%, 10% tolerance. Also, it's function of the temperature, it's function of many things. And because the RDS(on) value are not equally the same, the current will not flow equally in the different MOSFETs. And that will influence the losses and the junction temperature. Because if you have one RDS(on) that is, I don't know, 15% lower than the others, most of the current will go in this one. And even though you have different MOSFETs in parallel, you will still have a lot of heat and losses. And the best approach to study this is to run Monte Carlo analysis, where we run hundreds, thousands of simulation with different RDS(on) value, taking into account the actual tolerance of the value, and see what are the influences on the losses and the junction temperature. I see that the time is flying, so I'm going to go extremely quick about it. So here we have again a Python script that run the simulations, and we can see it takes about 40 seconds to run 1,000 simulation, which is kind of impressive, right? Because here we run a transient simulation where we simulate using description table, the losses in all the semiconductors. And it takes only 40 seconds to run 1,000 transient simulation with the settings. Okay, so to summarize this introduction to the dual-stage electro-thermal analysis, so the summary is, without any compromise on the accuracy of the simulation, the accuracy is conserved. We are about to achieve speed up ranging from 5 to 20 just by clicking on a button. And we hope that users will first understand the benefits and use this in their workflow. So for the dual active bridge, the speed up is about 20. For the motor drive efficiency map that I showed, it was 21. And for the Monte Carlo analysis, it's about a ratio of 5. So we're 5 times faster. And what explains the difference in speed up? It's mostly the difference between the time constants between the switching frequency and the thermal time constants. If the two time constants are very far away one from each other, the gain will be higher. If they are very close, there is not so much benefit of using it. But of course, there is always a difference between the two. And that concludes our introduction to the dual-stage electro-thermal analysis. We hope you liked it, and the introduction to SIMBA 25.03. We also fixed a lot of bugs and improved kind of the user flow, and we try to simplify a lot of things. So we hope you liked it. I think we have time for questions. I have seen some questions. Okay, let's.
Yes. Yes, we have a first question in the manual.
Oh,
So maybe can answer to the question is how I manage the time step of electrical and thermal bots for this new feature of the dual stage electro-thermal simulation.
okay, so time steps are very easy. So basically, it's two separated simulation. So the time steps can be different. The settings that you use, so for instance, in this motor drive here, we use a fixed time step, but in SIMBA, we also have a predictive time step solver. So we will use a fixed or predictive time step solver depending on the user selection. So for the electoral part, we will use the time step as a traditional variable time step analysis, where we have a minimum time step, in this case 200 nano, and we'll adapt the time step. Of course, for the thermal part, the time step will be way higher, right? Because we don't need to simulate the switching period. So this is how it is managed. I hope I have answered the questions. Is it okay? Oh, sorry, you were anonymous. We don't know who you were, so I hope I was clear. Well, what we have to remember is it's basically two different simulations with different time steps. And SIMBA will use whatever the user have selected, but if you use a variable time step, a predictive time step, that we recommend, the system will adapt to the time constants you have in your system. So okay, so then we have another question. Regarding the signal calculator, is it possible to manipulate signals from different simulations with different time steps? Yeah, actually, we have not mentioned that. But when you use the signal calculator, if the signals come from a different simulation or if it comes from a CSV file, because in SIMBA you can import CSV data, we take care internally of interpolating, extrapolating the signals. So we can actually calculate the expression. We can evaluate the expression with signals with different time data vector. Okay. So let me know if we have answered your question. Anything else? No. So I think we can call it today. Again, thank you for joining this webinar. Thank you for the team, Guillaume, Adrien, and everybody who help us developing 2503. You can download it already. It's available on our website. We wish you a very nice day. Cheers. Bye, everybody.
Bye bye.
Bye bye. Thank you. Take care.